variable length records. If you have variable length attributes, that will lead to variable length records. Okay. Any questions so far? Okay. So the way you organize variable length records on disk will be, of course, different from fixed length, and obviously will be a little bit more involved compared to the way we organize fixed length records. So I'm going to show you this diagram, then we will base our discussion on this diagram. So the idea of variable length record organization on disk, not on disk, on a page, is as follows. The basic idea is somewhat similar to what you have seen from the fixed length record organization, where you partition your page into two areas. One is called record space, the other is called free space. In this particular picture here, record space is that white space on top, and free space is that grayish area at the bottom of the page. And record space is occupied by records, and they are compacted together, leaving no space in between any two records. This is very important to note, right? Leaving no space between any two records. Okay? And at the end of the page, there's something similar to that bitmap array we saw from the fixed length record organization, but instead of using a bitmap to indicate whether a given slot has record or not, you can no longer do that here because you no longer have this concept of slots. Why is that? Because the records are of variable length. If I tell you slot 1, slot 2, you don't know where those slots are going to be. For fixed length, yes, I can. Start with the beginning of the page, slot 1, slot 2, because they're fixed length, I can do the calculation, figure out where they are. But for variable length, this doesn't work anymore. So you need a little bit more information than simply a single bit. So the idea is as follows. First, I store a pointer to the boundary between free space and record space. The pointer is represented as an offset value to the either beginning of the page or end of the page. It doesn't really matter how you do it as long as you are consistent in what you mean by offset value. To give you a specific example, suppose I'm using the offset value to the beginning of the page, and there are let's say there are exactly 500 bytes in the record space. Then the value of this pointer will be 501. Because the first 500 bytes are used by records. And the 501th byte is the beginning of the free space. So I will simply store that offset value here, serving as a pointer. Okay? Next, there's the value n to indicate how many slot entries in this slot array. So this is what we call slot directory or slot array. And this n simply indicates how many elements you have in that slot array. And followed by that is, n slot entries. If the value here is n, then there are n slot entries in this slot array. And we need to understand what each entry does. Each slot entry has two components. One is, as you can tell from the picture here, a pointer to a record. A pointer, as I explained just now, is an offset value to the beginning address of that record on that page. The offset is calculated with respect to the beginning of the page or the end of the page, as long as you're consistent in the way you're calculating this offset value. For example, the first record, imagine there's nothing, imagine there's nothing ahead of this record, so the pointer, the offset value will be 0, because you are essentially the first record of the page. There are no bytes ahead of you, so your offset value is 0. What about that second value here, or here? That indicates the length of this record. That indicates the length of this record. Now, given these two information, it's not hard to tell that we can easily figure out where a record locates at and where it ends. In other words, you can retrieve the content of the record without any trouble. Just use the offset value, go to that particular address on the page, read this many bytes according to the length of the record, you're done. You get the content of the record. Any questions regarding this?
So
Yes.
here in this bit or slot directory, each individual unit has
Each
only one
entry.
number. Each entry has one number. You said there are two components to it with
One is a pointer,
offset,
one is a
one
length. Yes, yeah. That's the two components I'm talking
But
about.
you didn't show it here, right?
Each slot entry has two components. One is the pointer, one is the length of the record. Okay. The other thing you want to a takeaway message from this picture is that the ordering of those slot entries in the slot directory do not correspond to the ordering of the records in the record space. Initially, if you think about it, initially they are. The first record comes to your page, I will allocate a slot entry for it. So the first slot entry corresponds to the first record. Second record comes to picture, second slot entry used for that, so on and so forth. So there is a one-to-one correspondence with the same ordering. If you only do insertion, yes, things will keep that way, and it's very simple and easy to understand. But you have to do deletion as well. You have to do update as well. In fact, you can model an update operation by deletion and then insertion. Any update can always be modeled as a deletion first, followed by an insertion. Delete of the record with the old content, and insert of the same record but with the new content in it. When you do that, the length of the record may have changed. Right? Keep that in mind. The length of the record may have changed. Or if you delete a record that leaves some hole in the record space, you have to do the compact operation as I mentioned. Right? Because you are supposed to have no empty space between any two records in the record space. And if you do that, and you do insertion afterwards, the ordering of the slot entries to the ordering of the record no longer follow the same sequence. Right? As you can imagine. I will demonstrate that using an example. So how do we do deletion? This is the offset. So let's assume we have this particular state of your page. Right? This is the one particular state of your page. The way you understand this is, can someone tell me what this means? 35?
Next week
Point to the end of the record space, beginning of the free space, which means the total record space now is 35 bytes, which basically corresponds to that very last boundary of the last record. 4 indicates there are 4 slot entries here. 35, what that means is the offset is value is 30, which means the address of this particular boundary is 30. 30 is 5. And the length of it is 5. So the math add up. If you do it, 30 plus 5, that gives you 35. That's why the end of the record space is 35. 10, 8, what that means? That means the beginning of address of this record is the 10th byte. And length is 8. So that the next one, the beginning address is 18, length is 12. That's why it's 18 plus 12, that gives you 30 right here. Finally, the last one, the last slot entry actually corresponds to the first record. The offset is 0 and length is 10. So everything add up is 1. Okay, everybody understand this? Or any question you have? Yes or no? No? Okay, let's proceed. Now, suppose I want to do a deletion. Well, final thing. I want to mention this record ID. Remember, record ID, as I mentioned earlier, is the page ID plus slot number. So the first record, the physical, if you look at the physical ordering of that, the first record on the page does not necessarily has a slot entry ID 1 attached to it, for the reason we just discussed. In fact, given this example, the first physical record on the page has a record ID of I and 4. Suppose the page ID is I. Why the slot entry value is 4? That's because the fourth slot entry actually indexes this particular record. That's why it's I and 4. The record ID of that is I and 4. Record ID is I and 2, I and 3, and I and 1. Okay? So this is something you want to pay attention to. It doesn't mean the first record on the physical level will have the slot number 1 indexing it. That's not necessarily the case. Okay. Now let's do some deletion operation. Yes.
Real fast, I might be getting this mixed up, but I thought on the last slide you said that the slot directory could be out of order as well. So how do you know the record order if the slot directory could be any record order?
Slot directory, the index of slot directory.
Okay, so that's always in that order of one stack.
The index is, of course, always is one.
Okay, but the records.
Yeah,
oh,
what I'm saying is
that's
the correspondence between records to the slot directory entries, these are not necessarily in the same ordering.
Okay, no,
That makes sense? Alright, let's do a deletion. So suppose I want to delete record I and 2. Delete I and 2, which is to delete this record right here. This record. Okay, can someone tell me what's going to happen first? If I delete this, what is supposed to happen? Brendan?
They're going to shift over.
You're going to shift on the compact space?
Yeah.
Okay. So those two records coming after this record will be shifted ahead of their original space. By how much? Someone said something. Yeah. But 8 bytes, right? Because the length of the record being deleted is 8. So you shift them ahead by 8 bytes. And that's exactly what happened. Shift them ahead by 8 bytes. But you're not done yet. You have to update these guys properly to reflect the new locations of those records being affected. First off, you need to update this value, the end of the record space. That's fairly easy, right? You take the original value, you minus the length of the record being deleted. That tells you exactly the new address of that. Because you are calculating this as an offset to the beginning of the page. Let me ask you this. If I'm using the end of the page to calculate my offset value, what happens now?
Going to add it.
You add 8 bytes to it. Right? So that iterates essentially my point earlier, which is you can use either beginning or end of page as the base to calculate the offset value as long as you are consistent. Doesn't really matter how you do it. Okay? Now, let's keep this for now. The slot entries are still 4. You are deleting a record, you are not deleting a slot entry. So this stay at 4. What about this value? Well, this becomes tricky, right? So among all these slot entries I have, I know one thing for sure, which is for each slot entry, I don't have to do anything regarding the length of the corresponding record, because those are not affected by the deletion of another record. The length of each record stays intact. But I do need to worry about the offset values. This is where it becomes a little bit tricky, right? Because the offset values of those slot entries are only affected if that slot entry corresponds to a record that actually is located after the record being deleted. Those records located ahead of that record being deleted, those offset values will not be affected. Because the compare operation is like this. Whatever happened before that record being deleted stay intact. Does that make sense? Once you figure out this, it's actually quite straightforward to figure out the update algorithm for the slot entries. You go through every entry, you look at their offset value. If their offset value is bigger, suppose we are calculating offset value with respect to the starting address of the page. If your offset value is bigger than the offset value of the record being deleted, what should you do?
Change it.
You should take, yes, you should change it, but specifically you should take the offset value minus away the length of the record being deleted from the offset value, because that's exactly how much you're going to shift them ahead. You do this for every slot entry. If the offset value is, however, smaller than the offset value of the record being deleted, what do? You do nothing about it. Does That's it. What about finally? What about that slot entry correspond to the record being deleted? Well, there are really two choices you can have. One is to deallocate this slot entry. But if once you do that, you have to shift all the slot entries coming after it as well, meaning you have to change the structure of the slot directory. But another approach, which leverages the following observation is, you have deletions, but you will have insertion as well. If I keep this slot entry floating around a little bit, I can quote-unquote recycle this slot entry for subsequent insertion operations. That's exactly what people do. So for example, 35 will become 22.5 because 30 is bigger than the offset value of that record being deleted. But this one, 10 and 8, is being deleted, and this 18 and 20, 18 is bigger than the offset value, so I will minus 8 from this. So I got 10, 12, 22 and 5, and 27. That's exactly what I got. But what about this slot entry that was pointing to that record being deleted? Well, you're going to recycle this. The way you're going to recycle this is reset its offset value and the length field to some default value that your program can easily figure out, oh, once I see this value, I know it's a slot entry to be recycled. So for example, -1, -1. No record can potentially have this length value or this offset value. So you know this is a slot entry to be recycled. Any question on this? Now the final point, the final special case is what if you delete this guy? You're not deleting this slot entry, you're deleting the record corresponded by this slot entry, meaning that first physical record. What happened? Well, you still need to update the offset value of these guys. So this becomes 0, this becomes 12, this becomes 17, because the length of record being deleted is 10. And this becomes -1, -1. Now this is a special case, because this is the last slot entry in your slot directory. By this time, if you deallocate or delete this slot entry from your slot directory, there are no structure change. You are simply deallocating the last element of your array. If you deallocate some elements in the middle of your array, you have to shift all the subsequent elements. But if it is already the last element, you don't really have to do anything for the structure of the array. And we actually do that. We free that slot entry, and at that point we decrement this value by 1. So this goes down to 3. But we only do that for the last slot entry to minimize the impact to the structure of your array. So far, so good. Any question on this? Yeah.
So it seems like if our strategy is to sort of just set a slot to a default value, when we come back and we want to do like scan operations maybe on this table, and we're looking at this directory, sort of at scale, when you have a lot of delete operations and a lot of these sort of empty slots lying around, that seems like it could become a problem as your database is going to figure it more. That's a good observation. What you're saying is, let me repeat the question. What he was saying is, if you have a lot of records, and then you end up and you subsequently delete many of them, so you have many of these -1 entries in the slot directory, and then when you do a scan operation, when you come back to a scan operation, would that be costly? Well, the answer is not really, right? Because this whole thing, if you think about it, is very small compared to the actual records you have. By the time you delete all those records, let's think about the extreme worst case, which is I only have 2 records. One is here, one is here. And in between, all those slot entries are -1. Now, in your record space, you actually have physically only 2 records that are compacted together. So what happens is you go to your slot directory, you linear scan that, which is fairly small, and you can quickly skip everything in between that has -1, -1. That's a good point. Even if it's a million, it's very small, right? So
yeah, and plus it's not going to be a million, right? Because a page can only fit. A typical record set is maybe hundreds of bytes, right?
Oh, okay.
Right? A typical page size is 4 kilobytes or 8 kilobytes. So if you do the math, you have about maybe around 100-ish records per page, or tens of records per page.
Okay.
So you have what? You have tens of up to 100 entries in the slot directory. There each is only 2 components, very small. And keep in mind, by the time you are doing this linear scan, this page is cache buffer. Alright, so that's variable length. The good news is, the bad news is, yes, this is somewhat complicated, more complicated than the fixed length record. The good news is you don't have to implement this. In the lab 1 assignment, you are implementing only the fixed length approach. Okay? So lab 1, if you think about what we discussed now, lab 1 is really the simplified version of what really happens in a database system. Okay, lab 1 only asks you to do, we used to ask people to implement variable length record. And starting from last year, I switched to this new version of project where it only deals with fixed length. But before last year, you actually have to implement fixed length optimization.
So are we going to do, like in a later lab, do variable length records?
No, we won't. But if you're interested, I do have a lab for that.
Maybe.
You can do it, but I'm not going to give you.
Right.
I'm not going to give you additional credit, but I will really, really appreciate your effort. If that means something, I mean, yeah.
I was just wondering, does that mean that deletion for variable length arrays is more expensive than for like very far structures?
Yes. Deletion of variable length will be a little bit more expensive. But keep in mind, all these operations happen in memory. So the difference, yes, there is some additional overhead, but it's not too bad. It's not too bad. You are updating, keep that in mind. All these update operation, all these insertion operation we talk about, you are doing this over a cache version of this page in buffer. You are not doing this directly over this page on disk. Right? So, there's no disk I/O involved. Yes.
All right, another question. It's easy to imagine an update operation where my varying character field goes from 12 bytes to 200 bytes.
Yeah. What happened to that?
Yeah, what happens there? Is there anything that gets
Yeah.
really complex, or is it just as simple as a delete and then insert again, or?
Okay. Excellent question. So the question was, okay, suppose I have, let's look at this. Suppose I have this. Now I want to update that second record, and it's variable length, and it happened to be I'm updating the variable length attribute of that variable length. So as a result of that, because if you're updating the fixed length attribute of a variable length record, the total length of the record stays exactly the same. But if you are updating the variable length attribute of a variable length record, the total length of record may end up being different. Right? So what happens? That was his question. You have two options if you think about it. One is, suppose the length got longer. What do you do? One option is to move whatever records coming after this record backward by the increment in the length of this new record. Then you can expand this record to the right size. Does that make sense? Do all of you follow me? By doing that, you need to shift all the record coming after it, meaning the offset value bigger than the offset value of this record. You basically do a linear scan of the directory entry and add the length increment value to the offset value of those directory entries whose offset values are bigger than the offset value of the record you are currently updating. You follow me? Okay, that's one option. The other option you may argue, which works okay in this case, because in this case only one record is affected. I'm shifting this one record. What if I have many records coming after this record being updated? Then I have to shift all of them. By the way, when you do shifting, there's one trick you should use. For example, going from here to here, you don't shift record one by one. You can, of course, do that, but that's super expensive. What you do is, you shift the entire memory space from this address all the way to this address, and you shift all of them ahead by the length of the record being deleted. That's very easy to do because I know the value of this is simply the offset value of the record to be deleted plus the length of that record. And the value of this is simply the end of the record space. So for example, in C++, that's just, you do man move. The starting address, and to the new location, new offset. Something like that, right? So you shift the whole thing to a new starting address. That's pretty much what you do. You don't move record one by one. Similarly, if you are expanding a record, you don't move all the record coming after it one by one. You shift all of them at once. Okay? Another approach, as suggested by him, is that, okay, I don't want to shift all of them backward. I'm going to delete this record, shift all of them forward, then insert a new version of this record to the end of the record space. That's another approach. Yes, you can do that. Delete first, shift all of them forward, insert at the end. You can do that as long as you keep one important invariant, which is after deleting that record and then subsequently insert a new version of that record, you make sure you use the same slot entry for it. Why you want to do that? Because you want to make sure the record ID stays exactly the same. You do not change the record ID of that record in this process. This is super important because record ID is an identifier system used to retrieve that record.
Then what do you do when we update which is too big for the page?
If you span over multiple pages.
Yeah.
Well, that's a really interesting question. I'm not going to discuss this online. It's a complicated discussion. We'll take this offline. For now, but that's an excellent question. For now, we assume this insertion update operation do not spill a record over another page. In fact, a simple answer to your question is, when that happens, I will make sure a record only resides in a given page. Okay? When that's not possible, for example, record length is already larger than the page length itself. What do you do? There are some special mechanisms people have designed to cater for those cases. So excellent question. Okay? I think that's all the discussion I want to have for the organization of record and so on and so forth. And toward the end of last lecture, I also talk about these things. I strongly encourage you to execute this SQL statement yourself against the PostgreSQL database server we have to get a feeling how catalog information are organized and how you can figure out the length of each record in the database. For example, let me clear this. For example, if I want to know the number of pages, number of tuples, number of attributes from the actor table, I can just do this. That tells you some basic information about this. If I want to know, for example, the size, the attribute length, and attribute type of a particular tuple, a particular table, let's say customer, I can simply do this. That tells me the attribute length, the type, and so on and so forth. Okay? So those are all stored in your catalog, which is something you are actually implementing in Lab 1. You are required to implement that catalog maintenance in your Lab 1 assignment. Okay, so that's that. Now let's change gear and move on to the next lecture. So next we're going to talk about access methods, access paths and access methods. By now, quick recap, what we understand is how data are organized on disk. Right? In a database engine. Really, the next step is how do I retrieve those data back? Once you play this somewhere, how do you get it back? It's kind of like now you understand when you say I'm going to open an account with Wells Fargo or Bank of America to store $1,000 how that $1,000 is stored. You know that information. But you will not be satisfied with just that, right? As a customer, you will be curious to know how do I get my money back? I want to make sure there's a way to get my money back, right? Access method to your money. Data is money, right? So that's essentially what we're going to talk about next. To do that, I'm going to introduce some abstract model first. Recall the discussion we had when all of your data reside in main memory. That's what we call the RAM model, random access model. However, the model here we are using is slightly different. We are involving a secondary storage medium, which is either a magnetic field disk or solid-state drive disk. Speaking of which, I should now give you that discussion on solid-state drive. What's the difference between solid-state drive and magnetic field disk drive? Very quickly, solid-state drive is non-volatile. So this is a really key feature of solid-state drive. That's why people can use solid-state drive for operating system, for database system. Right? You always need to use something that's non-volatile to store your system data and your database data. So solid-state drive is non-volatile. Secondly, it is much more efficient in terms of supporting random access compared to magnetic field drive. And that's probably the reason why people want to have a solid-state drive rather than having a magnetic field drive. Why? Because random access is much faster compared to random access from a magnetic field disk drive. You may wonder why is that? Why random access in solid-state drive is much faster? In fact, random access and sequential access from a solid-state drive, you almost see no difference in terms of the speed of it. But in our magnetic field drive, as we saw from the little experiment I showed you earlier, random access and sequential access has a huge difference in terms of the bandwidth, in terms of the throughput, the bandwidth utilization they have. Does that make sense? Yes or no? But on solid-state drive, the random access and sequential access speed are roughly the same. Why is that? Fundamental reason is there are complicated physics involving this, but fundamental reason is the way they represent bits 0 or 1 on solid-state drive is to use charged electrons units on that solid-state drive. In other words, you are accessing using, again, it's a very high-level sketch, but you're accessing those data using the speed of electrons rather than relying on some mechanical movement of head and so on and so forth. That's the reason why, that's the fundamental reason why it is way faster to access data from solid-state drive than magnetic field drive. Okay? Now, that being said, you may wonder why people still use magnetic field drive. Why don't we just go all to move everything to solid-state drive? Two reasons. One is solid-state drive dollar per byte is still way more expensive than dollar per byte on magnetic drive. Dollar per byte. Solid-state drive compared to dollar per byte from magnetic field drive. Meaning to store the same number of data, if you were to use solid-state drive all the time, you end up spending much more money than doing this on magnetic field drive. That's reason number one. Reason number one is important, but for companies like Google and Facebook and who have a lot of cash, they probably don't care. Because the more money you invest in your infrastructure, the more money you can make from your customers. But Google can now serve millions of queries per second rather than thousands of queries per second. Yes, I spend more on my infrastructure, but I make more money per time unit too when I'm interfacing with my customers. So at the end of the day, I still make more money. Right? So there must be something else holding that back. What is that something else? Well, deletion, meaning the other update, is expensive. Deletion on solid-state drive and update in other update operations are expensive. This has to do with how solid-state drive organizes data, how it does its updates. I'm not going to go into details, But in a high level, the idea is that you solid state drive organize a storage space into what they call a unit. Each unit is some kilobytes, like say 120, 64 kilobytes, megabytes, right? Some megabytes or kilobytes, depending on the configuration. Doesn't matter, some constant number of bytes as the storage unit. And the way it works is for sequential write, meaning writing data, initially writing data to solid state drive, that's easy. You write to something called buffer. This is not the memory buffer we just talked about. It's a buffer inside the solid state drive. This whole thing is your solid state drive. You write it here. Whenever this is completely filled, this is of the same size of your storage unit. You dump it to a unit. Then you empty the buffer. You do this continuously. Does that make sense? Now, updating, meaning I want to update, for example, this particular part from this unit. It doesn't support what we call in-place update. No in-place update on solid state drive. To update this particular segment, even if it's just 1 byte, what you have to do is to copy the content here to your buffer, change it to the new value, write to an empty available storage unit, and then do something called erase operation. We need to erase this so that it's available again. So that's the update process in a solid state drive. Does that make sense? All this play is expensive in terms of efficiency, but more importantly, the way it stores data is to use this special kind of electron fields, right? And the way the physics behind that is that if you do this erase operation too many times, this will fail. That storage media will just fail. Does that make sense? This translates to, if you do a lot of updates to solid state drive, the life expectancy of your solid state drive will be reduced dramatically. If you don't believe me, start writing the code and do random write and random update to solid state drive and see how long your solid state drive can hold. Personally, I will not do that with my solid state drive. But if you are interested in verifying my statement, you're more than welcome to do so.
You get extra credit?
If you have a failed solid state drive, I tell you what, if you're willing to sacrifice a 1 terabyte solid state drive, I will consider that. That's probably a few $100, but if you're willing to bet and use that kind of money, game on. Okay? But that's the point. Finally, the last point is, because of physics of it, the maximum capacity is still somewhat limited. Of course, you combine many of such units. Yes, one solid state drive. What I mean by that is, if you look at one particular solid state drive, the maximum capacity of that versus one single unit of magnetic hard drive disk, the maximum capacity of that, there is still a gap of that. Right? Typical solid state drive nowadays can support maybe 1 or 2 terabytes, but you can easily have a hard drive with 10 or even 20 terabytes on it. Of course, you can say, okay, I can buy 20 or 30 or more solid state drive to make up the difference. But keep in mind, when you have to plug in these guys into your computer node, right? On your SATA drive. Typically, they're using SATA 2 or SATA 3 drive. You have limited number of ports on a given node. So the maximum capacity per unit does play a role in setting up your clusters. Does that make sense? I hope it does. You cannot simply say, okay, I'm going to use 10 of this to make up the difference. You cannot. There is a physical constraint on that node. So that's another reason why solid state drive hasn't replaced magnetic hard drive yet. Let me continue with my discussion and I'll come back to the question. So, but the game is changing quickly. There's something called NVM, Can someone tell me, can someone make a guess what NVM stands for? Without knowing what it is.
Non-volatile memory?
Yeah, excellent. Non-volatile memory. You can be a good marketing person. Non-volatile memory, exactly that's what it is. So in other words, it is just like RAM, but it's non-volatile. It sounds like, that's exactly what we want, right? Memory, but non-volatile. That's exactly what we want. This is not available on market yet, on commercial market yet, but I think they will be released next year. Sometime next year, this will be available on commercial market. So once this is available, it will completely change, in my opinion, the design of database system and many other systems. Of course, there are limitations. I don't think magnetic hard drive will go away anytime soon. Because the capacity of it, I'm sure if you look at NVM, there are similar constraints as the ones we talked about for solid state drive. So it's hard drive, magnetic hard drive is not going to go away anytime soon, as far as I can tell. But you guys should keep that in mind. If you want to go out and work in this data management, large scale data, has to be large, right? If you're talking about a few gigabytes or even 1 terabyte data management nowadays, that's not large. That's like toy, in my opinion. Right? Like a few hundred gigabytes, that's nothing. It has to be in the level of terabytes or petabytes. That's what I consider to be large. Right? If you're in that space, you still have to worry about magnetic hard drive, you still have to worry about data transfer and all that stuff. You still have to be aware of the differences of different storage media and so on and so forth. However, if you are a data scientist to do data exploration on small scale data, like few gigabytes of data, don't worry about these issues. Use your RAM, that's more than enough. Okay? Now, with all that discussion, let's come back to access methods. So the way we model this, no matter whether you are using a magnetic hard drive disk or SSD, whatever that is, there is a difference in terms of access speed and access characteristics compared to access data from your main memory. No matter whether it's a magnetic drive or solid state drive, we know there's a difference. I want to model this, so it's different from the traditional RAM model we talked about earlier. So for that purpose, we're going to introduce a new model, which is highlighted in this picture, and pay actual attention to the parameters here, because we're going to use this parameter in the subsequent discussions. N is the number of items in the problem instance. So what that means is, if you are in the RAM model, random access model, N simply denotes the number of objects, main memory objects you have. For example, number of records you have. Okay? But if you are involving a hard drive or solid state drive, now note that the most basic unit of operation once you involve a hard drive is no longer just a record, it's a page. So N no longer stands for example, N can be used for number of pages, can be used for number of records as well. So you have to be careful in your analysis. When I ask you to do analysis, you have to be careful in the meaning of N, what N means. Does N mean number of records or number of pages and so on and so forth? Does that make sense? In our discussion, in the subsequent discussion, I'm going to use N, I'm going to fix the meaning of N to be number of records in your database. For example, in a given table. Okay? N is number of records in a given table. Doesn't matter whether it's the RAM model or what we call the secondary storage model, meaning disk is involved. N always refer to the number of records. B is number of items per disk block, or number of items per page. What that means is how many records you can fit in a page. For example, if my page size is 4 kilobytes and each record is 40 bytes, the value of B is what? 100. But if my page size is 4 kilobytes, my record size is 10 bytes, B, the value of B will change to 400. So B is determined by the page size and the record size, the relationship of the two. T is number of items in the output. For example, the value of T in this case is 2. Okay? And the value of T in this case is 4. That's the meaning of P. The size of the output, the interval measured by number of records. Okay? And I/O input and output stands for number of operations or number of access you have made to your hard drive. Either read or write. In other words, number of pages you read or write to and from your disk. That's what we mean by I/O. And M, capital M, is number of records you can fit in your memory. Number of records, not number of pages you can fit in your memory. And given that, how do I measure that using these values, right? Using those values over there, how do I measure the following? Number of pages in my main memory. Can someone tell me how to calculate that value? Number of pages in my main memory. M over B, right? That makes sense. Why? Well, M is total number of records can fit in memory. B is number of records fit in a page. So number of pages in memory is simply this, M over B. What about number of pages from your database? In a table, in your database table. Is this? It is total number of records from the table, and B is number of records in the page. So N over B must be the number of pages from that table. Okay? And we have this assumption that M is greater than B squared. You may wonder why we have this assumption. This comes in much later. So for now, just assume there's this assumption. We need this assumption for some analysis to hold. Okay? So now we just assume this. Let's look at some fundamental bounds in our analysis. Internal means the RAM model, meaning all the data fit in memory, which is pretty much what you guys have been used to so far. In all your computer science agitation, you by default or implicit will assume that's the case. You are using the internal RAM model. External means that you're in a real world scenario where data doesn't really always fit in memory. Some data will speed over to your disk, either a solid state drive or magnetic drive. What's the difference? Let's start with the simplest operation. The simplest operation is what? It's scan. Scan all records. What's the cost of that in your main memory? Scan all records. Well, you read record one by one. Does that make sense? You read record one by one. So there's N CPU instructions. So the cost of that is just N. N memory access. You're reading N records. Does that make sense? What about external memory? If you try to scan data from disk, what's the cost of that? Well, number of pages you have to fetch from disk to memory. That's the bottleneck. Of course, you can argue, once they are in memory, I still have to read record one by one. So the total cost of internet should be N plus B plus N. Yes, but be careful. The units of the two values are different. This is number of I/O you have to do. This is number of like CPU or memory access. And plus, of course, CPU instructions. Both of this, the per unit cost of this in time is much, much smaller than, this is in the order of nanoseconds. This is in the order of milliseconds. Right? So, you can ignore this, pretty much. The dominant cost is this. You follow my discussion? Okay. Sorting. What's the cost of sorting? In memory. Suppose you are smart, right? If you don't use bubble sort, if you use bubble sort, N squared. Oh, first element compare with all subsequent N minus 1. Second element compare with all N minus 2. So you end up with that's this, and that's N squared. That's bubble sort, right? That's bubble sort. But you should not be doing this, right? I hope you're not doing this, right? I mean, if you're doing this as a computer science major, then you need to you study on data structure and algorithms. Okay. What you should be doing is use something like quicksort, which gives you roughly n log n cost. On expectation, quicksort is a randomized algorithm. In the worst case, quicksort is as bad as bubble sort. Can someone explain to me why that? Why quicksort in the worst case is also n squared?
Pivot poorly such that you don't split the list into.
Yeah, if you don't partition, the whole point, quicksort is log n is because you do the recursion, right? Initially the list is n, you choose the pivot, recurse. Until each one reduces to just one. How many levels you have? If you have perfect partition, each level, which is partition down into 2, going from n to 1 only takes log 2n levels. At each level you do linear scan on the left and right, or linear scan at each sub-partitions, sum up them together. Each level is just n operations, so the total is n log n. But this analysis only works if your partition is perfect. If your pivot is poorly chosen, like this, you wasted one level. You're not doing any useful work. In the worst case, it's just n squared. You may wonder why people still use quicksort. It's the worst case n squared. Well, that's another complicated story. If you choose your pivot randomly, magically, it will just take log n steps on expectation. Why is that? That's another. I mean, I'm not an algorithm instructor, right? So you guys should go and if you're interested, you should be interested in knowing why, and I encourage you to go and read about that. So that's sorting. What about external memory? If I do sorting in external memory, of course you can simply use quicksort blindly in the external memory model. I randomly choose one record at my pivot, and when I do that, I have to pay IO to fetch the page containing that record. And then for each record, I scan them and pay IO. So I can pay n log n IOs to do this quicksort. Does that make sense? Yes or no? But it's super expensive. It's super expensive. And in fact, you might not be able to do that. What if after if you choose to pivot like that, it's not a balanced partition. This fits in memory, but this does not. You cannot even do the recursion when that happens. Right? So how do you do this? Let me give you an extreme case argument. Suppose you only have 1 kilobyte of main memory. Your computer has only 1 kilobyte. You may argue how is that possible? Okay, 1 kilobyte might be too much. Let's say you have. Let me see. When I was in high school, my computer was at the time it's cost 386 and 486. If that means anything to you guys, I don't know. Yeah, Intel Pentium 386, 486. That's the CPU at them, right? I think, if I'm not wrong, the memory size is it megabytes or kilobytes? Megabytes, right? I think it's maybe 4 megabytes. My memory is about 4 megabytes. I'm running 8 megabytes or something like that. I'm running Windows 3.1 on that. Windows 3.1 on that. Okay? And suppose you have 4 megabytes of RAM, and I ask you to sort 1 terabyte of data. How do you do that? You will say impossible, right? How can I do that? Right? Impossible. How do I do that? If I have 4 megabytes, it's kind of like your brain can only remember 10 cards, and you go to Las Vegas, and I ask you to memorize 1 million cards and sort them, but your brain can only memorize 10 cards, 10 values. How do you do that? The casino said, if you can do this, I'll give you $1 million. If you cannot, you're going to work for me for 100 years. What do you think? Before taking this class, you should say, no, I'm not taking this game. After this class, you should pretend it's a really hard decision, think about it for like a minute, say, fine, I will do it. Don't straightly say yes, because you see that, They become suspicious. They say, no, I'm not going to play the game. That makes sense? How do you do that? Well, the bound is like that, n over b log n over b, n over b. Why is that? We will analyze this later. Then there are permuting and sorting cost. I will come back to this later on. Okay, I will come back to this later on. To understand these bounds better, let me give you some simple games to start with. You all know queues and stacks, right? I hope you do. Queues and stacks. These are basic structures in computer science. What's the queue operation? Queuing operation. Push and pop, right? Push and pop. So if I push and pop from a queue, what's the cost of that in memory? You all know is order 1. Constant cost. Involve one operation. Is that right? If you do this in external memory, yes, you can still do this in one constant operation, but it's no longer just one CPU or one memory access, it's one I/O per queuing operation, either push or pop, which is fine, but not ideal, right? To push or pop one record, you need to pay one I/O to read or write a whole page of data. Seems like a little bit unnecessary, but the naive solution is just that. Can you do better? The question is, can you do better than one I/O for push or pop? Yes or no? Now, how many of you have done this experiment before? I'm sure some of you might have encountered this before, which is if I ask you to write a sequence of records back to disk in a file, not in a database set, right? Just as like you Java code or you C++ code. How would you do that? I want you to write a million records back to disk to a file that you have opened in your program. You fopen in C or C++ context. If you know C or C++, you know what I'm saying. Fopen, you got a file handler, and then you write. Is that the right way to write your code? Yes or no? If you run this code as it is, you will find it's very slow. You can buffer, that's the key word, you can buffer. What you do is, you buffer hundreds of thousands of records. Then you do buffer write or buffer read, meaning you are writing a page of data at a time. You don't write a record at a time to disk. Huge difference. Suppose each page can hold 100 records. The value of B is 100. To write 100 records, buffer writes take 1 I/O. Writing one by one takes 100 I/Os. The performance difference is 100 times difference. So coming back to the push or pop example, what should you be doing? Let me show an animation. Suppose now I'm changing from internal to external memory. So this white rectangular box and the boundary box, the yellow box and N no longer denote a single record but denote a page of records. They denote a page of record in the external memory model. What should you be doing? Instead of pop and push a record at a time, you should buffer them. In memory, you buffer. Remember, this page now cached in the buffer. You keep popping it until it's completely gone. Then you write to disk saying this page is gone. Similarly, for insertion, you cache this empty page to buffer, push until boom. Then you write one to the disk. What's the cost of this? Can someone do analysis for me? What's the cost of this? In terms of per record, what's the I/O cost per record for push or pop operation you have done?
1 over records per page.
Excellent. 1 over the number of records per page, which is 1 over B. Why is that? Because you are paying 1 I/O per B records. So your cost become 1 I/O versus 1 over B I/Os. So the improvement is about a factor of B improvement. And the value of B typically is hundreds. You can store up to hundreds of records per page. So your performance is 100 times faster by simply doing this for a queue data structure. Now imagine what if it's a more complicated data structure. Things become much more interesting, right? Even for queue, it's like this. What about for more complicated data structure? It becomes even more interesting. If you want to work for Google and Facebook and companies like that, never ever do this. In fact, if I'm you, I'm the guy interviewing you, if you do this, I will fill you immediately. Because with the amount of data Google, Facebook has, if you do this, it's not going to work. So you have to be aware of things like this. Does that make sense? But this introduces additional challenges. It's not that trivial, right? Yes, you can do this, fine. Like you can do this, right? Push, only then write to disk. But what if you have pushed 2 or 3 or tens of records, boom, memory is gone, it's power. Now I don't care about this 1 or B or 1 operation, I just care whether you have my data stored or not at this point. How do you cater for that? In the 1 I/O operation per record, you don't have to worry about this, because once you push, it's physically documented on disk, on a non-volatile storage medium. Huh? Does that make sense? And that's why that NVM is so attractive. But there are other factors you need to play trade-off with, right? Which I'm not going to go into details. Okay? But for now, let's assume there's something that's able to take care of this. You can push, you can pop in the buffer, and do 1 I/O per page without worrying about losing data if something happened, something disaster happened in the middle. How is that possible? There is some magic person doing some dirty work behind the scene for you that you don't have to worry about this. We will discuss that later on at the later part of this course. For now, let's assume there's something that's doing that for you. You don't have to worry about that. Okay? So that's Q. What about stack? I mean, the discussion is similar. For stack, you do this at the buffer as well, right? So the cost becomes 1 over B as well, for push and pop from stack, instead of 1 I/O per record. Okay? Now that being said, let's look at the heap file we talked about. Okay? Remember we talked about heap file in database, right? Now what we will do is essentially the same analysis, push and pop. But push and pop in the context of heap file is insertion and deletion. I want to analyze what's the cost of insertion or deletion, in other words, push and pop, in the context of heap file. Heap file is a more complicated structure than queue or stack. But the analysis we are about doing is essentially the same in spirit. Does that make sense? Okay? Alright. We're going to do the following analysis. We want to understand the cost of scanning everything, inserting a new record, deleting a record, and so on and so forth. Because those are the operations a heap file is supposed to support. Okay? And to make an analysis interesting, we're really going to compare 2 players. One is just a heap file, standard heap file. On the other side is what we call a sorted file. A sorted file is also a heap file, but records on that heap file are sorted according to a particular attribute or a particular set of attributes. What do I mean by that? For example, you have a student heap file, but students are sorted according to their student ID, from the smallest to the largest. So that's a sorted file with respect to student ID. It's very important to notice that a sorted file is sorted with respect to a given attribute. So in the earlier example, it's sorted with respect to student ID. But if I ask you to access that student heap file sorted with respect to student ID using student first name, it's just a regular heap file. It's not sorted anymore. Because it's only sorted with respect to student ID. It's not sorted with respect to first name or last name or anything else. That make sense? So keep that in mind. Now, what's the cost of scanning all records for heap file and for sorted file?
N over B.
It's just N over B. No matter whether it's sorted or not, if your goal is to scan all records, you have to read all pages. right? No matter how powerful, how mighty you are, or how smart you are, if I ask you to scan all records, go scan all the records. What can you do? I don't care what order you read them. Like, I want to talk to each one of you. Suppose that's what I'm supposed to do. Whether I talk to 3 of them first, then 3 of them at the back, or I just go one by one, this way or that way, doesn't matter. At the end of the day, you look at each record once, meaning you fetch all the pages once. So it's N over B. You know, the value of D is something the textbook uses. I actually don't like that term. D denotes the average time to access a page. This is really a fuzzy term because accessing a page, the cost of that depends heavily on, for example, whether it's a magnetic field drive or solid state drive, and whether it's a random access or sequential access. The value of D can change dramatically. So I don't really like this term D, but the textbook use that. So to make sure if you want to read the textbook and you understand what that means, I attach that term here as well. But in most of our analysis, I'm going to ignore that term D. Right? It's just an average, very fuzzy notion of how costly to access one page. N over B. And another thing that's important to note is whether it's heap file or sorted file, when your objective is to scan all records, you are doing really sequential IOs. Suppose these pages are sequentially located on disk, then you are basically sequentially reading them one by one. In other words, you pay one random IO to locate the first page, subsequently you sequentially scan all the remaining pages from that file. So the very first IO is expensive, but subsequent IOs are much more efficient than the first one because they are sequential IOs, except the first one. Does that make sense? Okay. What about I'm doing a equality search? So what do I mean by that? Equality search means that I want to find, for example, using the student example, I want to find student with student ID equal to 1, 2, 3, 4. One thing you note from my example is that student ID is the primary key. So by doing a equality search on student ID, I know there will be only one matching record. If there is one, right? It could be no matching record. So the number of records to be returned is either 0 or 1, but not more than 1. If you're doing a equality search on primary key, let's assume that's the case. Then what's the cost of doing equality search on key file? If you know that.
In the worst case, you have to scan all records, right?
Worst case, you have to scan everything. What's the best case? You're very lucky you find that record you're searching for in the very first page you read. And the fact that you can stop right after that is because you know there's only going to be one matching record. Once you find it, that's it. So the best case is 1, worst case is N over B. What's the average case? Half of N over B. What about if I do the same operation using the sorted file? Student key file sorted with student ID. It's log of what? That's important. Let me give you 2 choices. Log of 2n versus log of 2 of N over B, which is this. N over B. I'm doing IO analysis. You're doing binary search at the page level. You don't do binary search at the record level. So to be more specific, what you do, you load the page in the middle, the N over B divided by 2 page. And you look at the first record. If the value is there, you're done. The best case is still 1, right? But if it's not there, what do you do? If it's smaller than the first record, you know you can safely ignore all the pages coming after this page. You focus on your search only on the first half of your file, then you recurse. By log 2 of N over B operations, after this, in the worst case scenario, after this many operations, you must be down to only a single page. Either it's there or it's not there. So log 2 N over B is really the worst case. The best case is just 1. With that, I stop here. I will continue on Tuesday.